Alright, so today I'm going to prove a really cool property about linear differential operators, which is that they're microhypoelliptic outside of the characteristic set. So before we start, I'm going to need to define the characteristic set of a linear differential operator. So suppose we have an operator like this. So P of xd is the sum over all multi-indices with order less than m of these coefficients, which are smooth functions, and a differential operator here of order alpha, which is a multi-index. Alpha multi-index. And so I can define the characteristic polynomial of this differential operator like so. So P of x xi now is going to be equal to that same sum with so I have a alpha x, and we replace the differential operator with a xi to the alpha. So now this turns into a polynomial, and so this is called the characteristic polynomial, or the symbol of the operator. And now I'm going to define the principal symbol, or the principal part of the characteristic polynomial, which is the same thing except only the highest order terms. So I'm going to fix this the order of alpha to be equal to m. We have this. So this is the principal symbol of the differential operator, which brings us to the definition of the characteristic set. I'll call it VP, where P is the differential operator. It's going to be the set of all points x xi in omega, where let's say omega is the domain of the distributions where on which you will apply the differential operator. So it's omega times Rn. N is the dimension of omega without the origin, such that Pm, which is the principal symbol of your differential operator, is 0 on xi. So it's a set of roots of the principal symbol, right? Vp, your characteristic set, is a set of roots of the principal symbol. And this is a very important set, as it turns out, because we have the theorem that if U is a distribution on omega, then we have that the wavefront set of U is contained in the wavefront set of Pu united with Vp. So what this means is that we have microhypoellipticity, which is wavefront set of U is contained in the wavefront set of Pu. We have microhypoellipticity outside of Vp, and this makes sense if we take our intuition from substituting wavefront sets for the singular support, because we know that outside of Vp the operator is elliptic, and where it's elliptic it's also hypoelliptic. So in particular, this is saying that elliptic operators are hypoelliptic, and outside of the characteristic set they're hypoelliptic also. But it's saying more. It's saying now that we have microhypoellipticity, so we can substitute the singular support for the wavefront set and get the same assertion. Okay, so before we prove this theorem, we're going to need to actually define this thing called a microlocal parametrix. So we're going to need to define a microlocal parametrix, and this is going to help us greatly in the proof. So to define a microlocal parametrix, first of all, actually we're only going to prove the theorem for P of constant coefficients. It's also true for variable coefficients, but that is a much harder proof. So let's stick to the constant coefficients for now, and let's fix a xi0 such that Pm of xi0. Notice that the principal symbol now only takes one input, because it's it only really depends on xi now that we have constant coefficients. So fix xi0 such that this is not 0. So we're taking xi0 outside of the characteristic set of P. So we fix this psi 0, and now notice that since this is not 0, we have Pm of psi 0 normalized is also not 0. It's also not 0, and by the constant, so this is going to be a point in Sn-1, right, in the sphere. And since this is not 0, and by the continuity of Pm, we have that there exists a neighborhood U0 in S of n-1, so S of n-1, such that, well, first of all, this guy is containing U0, and, so let's write that, this containing U0, and P then of Pm of xi is, let's say, greater than or equal to some constant C for psi in U0. Okay, this is just from continuity of Pm. And, okay, so we can now define, let's define a cone, let's call it gamma 0, let's call it the cone gamma 0, the cone of xi in Rn without 0, such that xi normalized is in U0. So if we have S here, and let's say this is our U0, then our cone xi is going to be this cone here, right? You kind of project that neighborhood outwards into a cone. So what do we have now? What can we say about the values of Pm on this gamma 0? So we had that Pm of xi is greater than or equal to C if we were in that U0. So let's suppose that we have some xi in gamma 0 now. Well, we know that xi divided by its absolute value is going to be greater than or equal to C, right? By this. So by the homogeneity of Pm, we can actually pull this guy out. So this is going to be equal to 1 over this to the m xi is greater than or equal to C, and then we can bring this guy to the other side. And we have this. So this is a nice little bound on the symbol, the principal symbol, but it only holds here, right? It only holds on this cone. And we can actually get a similar thing for the whole symbol, right? For P xi, not just Pm xi. And the way we can do that is like this. So we can write P xi is equal to P xi minus, so we just sum and subtract Pm xi. And here we use, let's see, what do we want to use, the reverse triangle inequality or the triangle inequality? Okay, so here we use actually the reverse triangle inequality to show that. So we have P like this. Right. So we have this, and by, so actually we should probably, to make this easier, we should write let's write there. So that's the same thing, but this will make our life easier, because now we can write this by the reverse triangle inequality. And great, so now we're in a position to start bounding this. By this bound here, we can bound this guy below by C xi to the m. And now to get a bound below on this entire expression here, we would need to get a bound above on this guy, right? Because we have this minus sign here. So this guy is bounded above. This guy is bounded above by. Well, this is note that this is a polynomial without its principal part. So that means it is a polynomial of degree m minus 1. And a polynomial of degree n minus 1 is O, so this is O of xi to the m minus 1, meaning that there exists a radius r greater than 0, such that for every xi greater than or equal to this radius, there exists radius, also there's this radius, and there exists a constant greater than 0, such that for every xi greater than this radius, we have that p xi minus pm is less than or equal to c times xi to the m minus 1 for every xi, for every xi greater than this radius, right? So we can bound this above by c xi m minus 1. So this is, I guess, another constant, so I'll call this c prime. And yeah, so now what we have is, so all of that is greater than or equal to c xi m minus c prime xi m minus 1. And now we can just pull out this guy. So this is going to be equal to m c minus c bar 1 over xi. And so now we can take r. We can now take r to be sufficiently big. So r sufficiently big such that this is sufficiently small. Let's say it's just smaller than c over 2. Because if it's smaller than c over 2, then or let's say it's small enough so that it's equal to, let's say, so smaller than c over 2. So smaller than c over 2. So then we can bound all of this. So if psi is greater than this new r prime, which we can just call r again, then we have that this is bounded below by this by xi m times c over 2. Great. So now we have this bound, right? We have that the symbol for the differential operator is bounded below by this this thing that grows like a polynomial here, and so now we can start building our microlocal parametrics. Okay, so yes, and of course this bound is only valid for xi greater than the r that we established, and this is greater than r. What else we had? Oh wait, we had xi also in gamma 0, so xi has to be greater than r, and xi in gamma 0. Right, these two conditions are very important. So the purpose of defining our microlocal parametrics will actually be to cut out a piece of this polynomial that is always inside of these conditions. It's always inside of these conditions, so that we always have this bound, basically. Or better yet, the main point is that so at least this guy doesn't go to 0, right? So at least p doesn't go to 0, because our intention is going to be to multiply by 1 over this polynomial, and so the bottom part can't have any zeros, and so we define a microlocal parametrics in a way that cuts the parts of the domain where this guy might be 0. Okay. So this will make more sense, I guess, in a second. So to define the microlocal parametrics, we first define a chi. Chi is a test function, c infinity c, in Rn, such that, let's say chi is equal to 1 on, let's say chi is equal to 1 on a ball of radius, let's say r prime, which is slightly less than r. And the support of chi is in a ball of radius r. Okay, and so this is the first thing we define. The second one is h. So h is another function, c infinity c of Rn, such that, define h such that h is equal to 1 on gamma 1, where gamma 1 is an open cone with closure inside gamma 0. So gamma 1, closure in gamma 0. So h is going to be equal to 1 on there, and the support of h is contained in gamma 0. Okay, so if this is gamma 0 and this is gamma 1, h is 1 here, h goes to 0 here, and h is 0 everywhere else. Now, actually, we have one more condition for h, which is that h is positively homogeneous. And what that means is, for every lambda positive, we have that h of lambda xi is the same thing as h of xi. So this means that every radius is a level set of h, basically. H doesn't change values along any given radius, and this will be important later. So we probably define h, actually. If we want it to be continuous, we can define it on Rn without 0. If we define it on Rn, it won't be smooth, but it won't matter because it won't matter for the sake of our integration later. Okay, so now that we've defined these two functions, chi and h, we can define the symbol of our parametrics as, let's define the symbol q of xi as h, so h of xi times 1 minus chi of xi times 1 over p, right? So this, what this means is we have gamma 1 and gamma 0 here, and our radius, the radius r. We know that outside of the radius r, chi is equal to 0, so 1 minus chi must be equal to 1. So here chi is equal to 1, and we know that inside gamma 1, h is equal to 1. So in here, both of them are equal to 1, right? In this cone here, both of them are equal to 1, and this is where we care about them. Outside here, everything is 0. Everything is 0 outside here. And where else do we have 0? Yeah, just outside here we have 0. And so inside these values, no, this is between 0 and 1. And over here we have, again, values between 0 and 1. Yeah. So, okay. So this is what this means. We've cut off the domain of this guy to essentially only the parts that matter, which are the parts where it's sufficiently big. And so we can define our parametrics now, QD, as actually QD of V, where V is a distribution, a tempered distribution, and this is equal to the inverse Fourier transform of Q of xi times V hat, right? So this is our microlocal parametrics. Okay, it's like an attempt to invert. It would be an attempt to invert P of D, right? So if V, for example, were equal to P du or something, then this guy would be trying to invert PD. Okay. So now we can start our proof now. We can finally begin our proof of let's rewrite the assertion. The assertion was that the wavefront set of U is contained in the wavefront set of PU united with VP. And remember that we already chose, to start off with, we chose a xi that's such that Pn of xi 0 was not 0. So this psi is already not in VP, right? This is important because the strategy will be to prove the contrapositive here. We want to take a point x0, xi0 that is not in this set, and we want to show that it must not be in this set also. And that'll prove what we want. Okay, and so we already started off, so this x0 doesn't matter that much because we're in constant coefficients. So let's just fix some any x0, and we fix our xi0 such that we're not in here. So now we only need our xi to choose our xi0 such that we're also not in here. So let's do that by assumption. So suppose x0 xi0 is in the regular set of PU. The regular set is just the complement of the wavefront set of PU, which means there exists a phi cutoff function, which is a C infinity C function, which equals 1 on a neighborhood of x0, a cutoff function, such that phi of PU has a Fourier transform that decays rapidly on the cone gamma 0. Now, this gamma 0 doesn't a priori have to be necessarily the same as the one before, but we can suppose that they're equal because, for example, if this one was smaller than the other one, then we could have chosen the other one to begin with to be smaller. So if this is a different cone than our first gamma 0, we just take the intersection of both of them and define both of them as that intersection. So suppose this actually is the gamma 0 that we had before, and we have this phi fixed. We would like to show now that that x0 xi0 is not in this wavefront set, so that u decays rapidly along that direction. Okay, and so our strategy will be to write QD PD phi u as phi u minus some distribution A minus some distribution B, and showing the rapid decay of u hat on the direction that we want. For the purposes of showing that the direction is in the wavefront set, it's the same as showing that this guy decays rapidly, that the localized u decays rapidly as well. Okay, so if we can show that A decays rapidly in the direction we want, B decays rapidly in the direction we want, and this whole guy decays rapidly in the direction that we want, then we have that this one decays rapidly in the direction that we want. Because this is from a property that we know the wavefront set of some distribution A, the wavefront set of some distribution A plus some distribution B is contained in the wavefront set of A union with the wavefront set of B. And if we take the complement of all this, right, we invert this contains, and using De Morgan on the right side, we have this. But the complement of the wavefront set is just the regular set. So the regular set. And this will give us what we want, because basically these A, B's, we can have another C over here or whatever, are these guys. And we're writing this is our sum. So this guy is our sum. So if we show that a direction x0 xi0 is in the regular set of this guy, this guy, and this guy, then it's in the intersection of the regular sets of all these, right? So that means x0 xi0 is here, and so that means it must be in here, which is the regular set of what we want. Okay. So by these inclusion properties of wavefront sets, this strategy will work. So all we need to do to finish is show that x0 xi0 is in the regular set of this, this, and this. But first, let's get this expression. So to get this expression, we just write down this, which by definition is equal to f minus 1 q xi of the Fourier transform of this, which is equal to f minus 1 this, and then over there we have 1 over p hat. We have Q of psi was h of 1 minus chi of 1 over p, like this. By the properties of the Fourier transform, we pull that derivative out like a polynomial, and then we have here, right? This cancels out with this, and then if we distribute that Fourier transform of phi u, we get this minus h psi u, right? So if I didn't make any mistakes, this is right, and by the linearity of the inverse Fourier transform, we have this. H psi. Okay. And so yeah, I think this is just about it. So on this, actually, yeah, so this one we can actually continue to expand. Let's write that as f to the minus 1 of h phi u minus phi u plus phi u, which by linearity again is equal to phi f of minus 1 of h phi u minus phi u plus the inverse Fourier transform of the Fourier transform is nothing, so it's just phi u. Okay, so then we have that equals this, right? This guy over here equals this. And okay, just so we get a minus, just like we did up here, let's switch the signs here. So we have minus and plus. And yeah, so now we basically have this expression, right? Let's rewrite what we have until this point. We have QD PD phi u equals phi u minus the inverse Fourier transform of phi u minus h Fourier transform of phi u, and then minus the inverse Fourier transform of h chi Fourier transform of phi u. Great. Okay, so that's what we have. That's what we had up here, right? Except more precisely. So let's just show that this is smooth in a direction. We need to show that that all these three are smooth in that same direction. And let's call them 1, 2, and 3. So let's call this one 1. Let's call this one 2. Let's call this one 3. They will all be smooth for a different reason. So let's start off by proving that 1 is smooth. So 1 is smooth because because of the convolution property of the Fourier transform. We actually have that is equal to, that 1 is equal to f minus 1 to f of minus 1 of h chi convolution with f of minus 1 of the Fourier transform of phi u, which is just phi u. And notice that this is a distribution of compact support, and this is the inverse Fourier transform of a test function, which is of course smooth. So this is in C infinity, and so by the convolution properties, this is going to be C infinity on Rn. And so yeah, so this is the best case possible. It's just smooth everywhere. So for 1, we finished. This is the easiest one. Let's go to number 2 now. So for number 2, we need to use the Leibniz rule. So QD of P d phi u is actually QD of, so we have to use the Leibniz rule here. So this is going to be equal to alpha less than or equal to m, sum of alpha less than or equal to m, of a alpha, right? These are the constant coefficients, times, this is where we use the Leibniz rule, beta less than or equal to alpha of alpha choose beta, d alpha minus beta of phi d beta u. Okay, so now we can use a trick. To pull out only the terms of order beta equals alpha here. So we can write this guy as for the term of beta equals alpha. We have say phi d alpha u plus the sum of now beta only strictly less than alpha, of the same thing, right? Of the same thing. And so now we have to distribute this guy over this sum. And what we get is, so we have QD applied on just this whole mess here, which is, I'm not going to write these indices of the sum to make my life easier. So this is A alpha times phi d alpha u. I can pull this phi out actually, because there's no, we're not summing over anything there. U, and what else? So we have plus, we have two sums. One is over this index, the other one's over this index of A alpha, right? E alpha is outside, right? A alpha, alpha beta, all that stuff over here. Okay, so then we have these guys, and we can use the linearity of QD to put QD here and to put QD here. Okay, so interesting thing about this guy is that so now that we have these two guys, we're going to use our facts, right? Oh, I didn't mention the facts about QD. So maybe I should do that now. So there's two important facts about QD. One of them is that if V is every time we apply something, QD on something, it's going to be a temporal distribution. So if V is a temporal distribution, and V is a temporal distribution, we have that the singular support of QdV is contained in the singular support of V, right? So this is like a pseudo-locality kind of. And we have another property, which is kind of like a Paley-Wiener theorem for this circumstance, which is that if V hat is rapid decay on gamma 0, then if V hat is rapid decay on gamma 0, then QD of V is C infinity, right? This is C infinity. So you have these two facts, and by fact number 1, we can show that this guy is smooth, because notice that this phi, notice that we never take derivatives of order 0 here in this guy, because beta is always less than alpha. And this phi is a test function. And not only is it a test function, but it's a test function that equals 1 on some below some radius r prime. And it equals 0, right, after some radius r. So this little circle in the middle is the only part where phi actually varies. So the derivative is always going to be 0 in here and 0 outside of here. Meaning the singular support of this whole guy here, of this whole guy here, is only contained in this annulus here, right? And so if we consider that V is this guy, then QD of V, which is this guy, has a singular support also contained in this annulus here, meaning that it must be smooth. In this little inner ring, which is it's an inner ring that contains x0, so we're good, right? It's smooth in all directions around x0. So by this first fact, we have that this guy's smooth. And now to show that this second guy is smooth, we just use this fact here, because so if V hat is a rapid decay on gamma 0, and in fact V hat, if this is V, then V hat by assumption, right? Because this is just PD of U. So by assumption, we had 5 PD of U is rapid decay on gamma 0, and that means that QD of V is, of course, C infinity everywhere, right? So this term is C infinity on the ball of radius r prime, and this is C infinity everywhere. So now we're only left with we're only left with this number 3. Right? Let's go for the home stretch here. We only have to show that this one is C infinity on the direction we want. Let's go to number 3, which is Fourier transform, inverse Fourier transform of this minus this. Okay. And first let's rewrite it. Like let's just distribute this phi so we have 1 minus h. Okay. And now let's prove that this is actually smooth in the direction we want for all substituting this for some v of compact support. So let's take this compact support, and our proposition is that if this is substituted with this v of compact support, then this will always be C infinity on x0 xi 0. Okay. So yeah, let's get started then. So we can define, let's say G is equal to this. Say G is equal to this, just to make notation easier. And remember, if we want to show that G is C infinity here, we have to define a cutoff function psi. Let's define a cutoff function psi, cutoff function around x0 that equals 1 on some neighborhood of x0. And now we analyze the Fourier transform. So analyze the Fourier transform. And so this is going to actually be equal to, by the property of convolution of Fourier transform, it's going to be equal to 1 over 2 pi to the n times the integral of, let's say, eta in Rn of phi xi minus eta, Fourier transform here. And on the other side, we also have the Fourier transform, but that cancels out the inverse Fourier transform. So we have this eta times 1 minus h of eta d eta. And okay, so since 1 minus h, note that it's 0 outside of gamma 1, right? Is that correct? So maybe it's 0 outside of gamma 0. So that means eta is not in gamma 0, right? We can take this restricted domain of integration, no problem. And what else do we have here? So this is not in gamma 0. And notice that we can now define delta greater than 0 such that, if xi is in gamma 1 and eta is in gamma 0, is not in gamma 0, then xi minus eta is greater than or equal to c xi. And what this means basically is if we have gamma 1 and gamma 0 here, that if we choose xi here, then we can always find delta small enough such that if eta is outside of gamma 0, which out here, then this ball will not contain eta, right? So this is I guess a fairly intuitive assertion. So we define this delta small enough, and now we can go ahead and use the Paley-Wiener theorem, right? So notice that this is a distribution of compact support, so the Paley-Wiener theorem says that this must grow at most polynomially, and this is a distribution of compact support. So, this is a test function, so the Paley-Wiener theorem says that this must decay rapidly. So we have that this guy here is less than or equal to, just let's forget about this constant, let's put this constant over to the other side. We have this times the integral of eta not in gamma 0 times Cn 1 plus xi minus eta to the minus n, to the minus n, and then we have some c 1 plus eta to the m, where m is some positive constant, 1 minus h d eta. And over here, we can substitute this with c xi, right, because of this. So we just substitute this with c xi, and we can pull this c out of here, right, by just standard analysis arguments. So this is going to be c to the minus n, which is absorbed into this constant. And now, simply, so this is the part where it was important that we chose h positively homogeneous, so it doesn't ruin the convergence of this integral, right? H is basically for the purposes of bounding, we can assume it's a constant because it's a constant on every radius, and of course, you can only assume distinct values on the sphere s minus 1, and s minus 1 is compact, and so So this is a continuous function on this compact domain, meaning it has a maximum value. So we can just take that maximum value to be the upper bound for this guy. Right? That's pretty cool. And so this is basically a constant for the purposes of integration, at least. Right? We have these guys that will control the decay. And now, if we choose an appropriate n, we can just pull this guy out of the integral, since we're not integrating with respect to eta, and such that we have sufficient terms left over to make this guy actually converge. So in the end, we do yes. So all of this is valid, of course. Yes, all of this is valid here, right? So we took xi in gamma 1. So gamma 1 is the cone where we have rapid convergence, and it doesn't matter because xi 0 is also in gamma 1, right? And our cutoff function was psi. So for psi cutoff function and for gamma 1 cone, we do have rapid decay of this Fourier transform, which means that our term number 3 was also C infinity on x0 xi 0, which proves the theorem.